of this also. Okay, let me start our lecture for today, and I would like to start with what we are going to have in the midterm examination. The midterm examination going on Sunday, May the 16th, starting at 8 p.m. until 9:30 p.m. That means we are going to have about 1.5 hours, 90 minutes for like 60 to 70 problems. Okay, let me first start with this presentation. There are many questions in the examination, so I like you guys to plan very well on your work. And the problems, some are very easy, some may require you do some computation, so you got to prepare everything. But I suggest you guys to do a short note on A4 paper, 1 or pages, in order that when you read the question, you will go to the paper and you can see the note, and you can find the answer very easy. Okay, let me start. This is the old questions that I took from your friends' examination and your senior examination. The problem is kind of easy. The first one, I just asking you which one is going to be the answer of this. You may type in if you prefer. Can you? Which one is going to be the answer of this? Anybody can type to show me on this? That is going to be what? The one that following the reg.sut.ac.th. The answer is supposed to be material testing here. Okay. And then we come to the chapter 1. That's going to talking about the presentation of the testing result. The first question about the chapter 1, what is not the content of the laboratory report? You supposed to answer this one correctly, because everybody have written the laboratory report. And then you can see when you start it, you got to say about the statement of the problem, like you're going to take the laboratory number 3, that is going to be the tension test of the steel and the cast iron. And for sure, you also going to talking about the material, but you are going to talking about the material, but it's going to be an testing method. It's going to be something like this. So this is not be in your laboratory report. It's not complete. It's not only the material, it's the testing method also. Okay, and then the report gonna include the summary of the test result, the conclusion and the discussion, and the appendices. Okay, and next, when we work on the laboratory, we gonna compute a lot of things. For example, this one is the normal stress, and the normal stress can be both in tension and in compression, for example. And that is symbol that we use. Okay, and for the A, you know this. Which one? Could you answer me? This is going to be the Poisson ratio. Okay, and the Poisson ratio is minus of the lateral strain divided by longitudinal strain. And the second one is what? This one is the shear stress. We have tau equal to V over A for the direct shear, or tau equal to VQ over IT for the transverse shear, or tau equal to TR over J for torsional shear. Okay, you guys can remember about this, right? And then we come to this. This is going to be the normal strength. And then we have the normal strength equal to the delta divided by the length. Okay. And this is what? This is going to be the density of the material. Okay. For the steel, we have the density of what? The load of steel equal to 7,800 kilogram per cubic meter. Okay, and if you're talking about the load of the concrete, that is going to be approximately 2,400 kilogram per cubic meter, or it's going to be 24 kilonewton per cubic meter. Or this one is going to be about 78 kilonewton per cubic meter. And then you know that this is not the symbol we are using for the mechanics of material. Okay. And then we come to number 4. This is important. This is going to talk about why you are going to learn this course. It asks you about the objective of this one. Okay. When you talking about the cost of material testing, we are going to talking about the mechanical properties of material. We talking about various of it, such as sigma sub u, such as sigma sub y, such as the modulus of elasticity. And then you use what? We are going to use this in the analysis and design of the structure. Okay. And the second thing, not only knowing of the mechanical property of the material, you also must know the testing method. Okay, testing method for the material. That is going to follow the Thailand Industrial Standard or the ASTM, American Society for Testing and Material. So which one going to be the answer of this? Well, the main objective is just to investigate the strength of the material. That means you just investigate the sigma sub y, that's not enough. Okay. To use the obtained data in construction of the building. Yeah, that is some, but not really the one that we really focus to obtain the mode of failure. That is just part of it. Okay. And to check the material is good or not. Okay. That is going to check with the TAS. Okay. But the last one is the answer to use the obtained data in the analysis and design of the structure. We use this to compute the sigma allowed equal to sigma sub y by factor of safety. And then we use this in the design of the structure and then in the construction of the building later. Okay. And then here comes problem number 5. In this course, what do we need to learn? Okay. We learn a lot of things. One is we learn about the behavior of the material. The second, we learn about the method of testing or the testing method. And then we also learn about the mode of failure of the material, such as when you do the tension test. Okay, tension test, you know the failure of the steel gonna have a kind of necking. Okay, which is different if you test for the cast iron, that is going to separate into 2 pieces. That is about the mode of failure of this. So for the cast iron, the failure gonna be abrupt failure, but for the steel, the failure is going to be the progressive mode of failure. This is going to be progressive mode of failure because the steel is a ductile material. Okay, but the cast iron is the brittle material. So the cast iron will have abrupt failure. Okay, and then the answer is going to be all of the above. Okay, not only the first two. We are going to study the behavior, the mechanical property, the mode of failure, and the method of testing. This is going to specify in what? In the standard, such as in the Thailand industrial standard. Okay, and next we come to the problem number 6. Okay, that is going to be still on the chapter number 1. And then if you are as an engineer lack the knowledge about the mechanical property, about the knowledge of what? Of the material testing, about the method of testing, and you also lack the knowledge of the mode of failure. Okay, what may be happen to the structure we work with? As I mentioned about 2 things, if you not have the proper knowledge about the material, you may what? You may cause the aesthetic. No, this is a beautifulness of the thing. So this is not the answer. It may be, the structure may not be utilized as planned. That's a part of it, but not really impacted. Okay, and the structure may be constructed harder. It's not really that's one, but for sure, if you don't have the knowledge of this, you may be analyze the structure wrong. You may be the design the structure in the wrong direction, and then it may cause the damage to the structure. Okay, I think this one is going to be the answer of this. And when we come to the mechanical property and the method of testing, we talking about the TIS, which is the Thailand Industrial Standard. It is the legal thing. You got to follow this. And they said how many types of TIS? TIS have some symbol. One have a symbol in the circle. Another one just have no circle. We have 2 of them. This one is legal, such as when you produce the steel, you're gonna follow the TIS. But for some construction product, such as the pre-stressed concrete pipe, you don't need to have the one that have the circle around it. Okay, just have the symbol of it. I don't have the this one. I don't have the symbol here, but you can go back to the lecture and you can check. There is 2 of them. One is the legal one. This is obligation to do so. Another one is just a choice. You just do it. If you do it, it's a good product. Okay. If you don't do it, it's okay. Okay, that is the example that I may ask you for the first chapter. Okay. For the second chapter, that is going to be the analysis of data. The first one, if we have many specimens to test for the strength of the material, what kind of statistic distribution we are going to talking about? This is going to be the simple distribution, summation distribution, normal distribution, Newton distribution, or Bell-Desk distribution. You know what? Where we have to test a lot of specimens, you will get to have this kind of distribution of the data, and then we can determine the average. We can determine the standard deviation. and we can compute for the normal distribution. Okay, and then if you do the test and then you get some data, for example, you get the data of 24, 21, 12, 17.5, 4, 1.5, can you compute for the mean of this? This is going to be the x bar, going to be 24 plus 21 plus 12 plus 17.5 plus 4 plus 1.5, and then you do the average of it, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, and 6. Okay, you just compute it easily. And also, I ask you to determine the standard deviation. You can use the calculator to compute it easily, right? And there are a lot of things that you're supposed to be able to do on this. This is just the example. Okay, I left this computation for you. Since you have your calculator, it's going to be very easy to do so. Next, let me come to the problem number 12. On the problem number 12, accepting, okay, not only we compute for the mean of the yielding stress, compute for the standard deviation, we also have another thing that we got to compute is the coefficient of variation. The coefficient of variation is going to be the x bar divided by the SD and times 100%. So the value of this is going to be 100%. And this is going to show the quality of test, quality of the test, the test TEST. Okay, this show the quality test. The test for this kind of yielding stress, the coefficient of variation supposed to be less than or equal to 7.0. If you compute this, you're going to get it for 45 and divided by 610 and then times 100%. By this, you're going to get this one for 7.38. And since this one is larger than 7.0%, so the quality of test is not acceptable. We have, oh, sorry, the equation is wrong, sorry. It's going to be SD divided by the X bar, okay? SD divided by X bar. So this shows us the higher than standard coefficient of variation. You should go to the PowerPoint and see this kind of value in a table, okay? And then come to the number 13. For example, again, we have the mean, we have the standard deviation, and they just ask us again to determine the coefficient of variation. You can do so for sure on this, okay? And then the 14, on the problem 14, this just what asks you, what does the sample standard deviation of a set of data represent? Okay, let me say for the mean, the x bar represent what? X bar represent the average, the center of the data. Okay, but there is different type of normal distribution basis on this. If the data is good, all of the test results supposed to be get very close to each other. Okay, for this one, you're going to get low coefficient of variation. And then for this one, you're going to get a higher coefficient of variation that show a large distribution of data. Okay, so The sample standard deviation will show us about the distribution of the data. That is going to be the variation of the data from the sample mean. If you get larger, okay, standard deviation, that's you mean you're going to get larger coefficient of variation. Since the coefficient of variation and the standard deviation, they are proportional to each other. Okay, so this one show us the variation of data. We like to have the normal distribution like the one or the data just getting close to each other, and we really don't like the distribution of the data like this one. That's going to be very large distribution of the data. Okay, and then coming to the relationship between the reliability and the probability. Coming to what we have on the data, okay, and if you have the data like this, and you said you're going to talking about the average, okay, for the normal distribution, the value here is going to call the C value, okay, and the C over here gonna be 0. That's represent the mean of the data. And then when we talking about the statistic to analysis, the mean, when we use the mean of the data, it means 50% is going to be fail, and another 50% going to be passes. And to make your mechanical property more reliable, most of the time we must minus the mean by some specific value of the standard deviation. When you minus it with one standard deviation, you're going to get this area of 85%, about 85%. That means about 85% of your specimen gonna pass this value. When we doing this portion, we call it reliability of the data, okay? And then the other rest of it, that is going to be the probability to failure. This is going to be about 15%. So what we have, the relationship is going to be the R plus P is going to be 1.0. So it's going to be this relationship. And then coming into this, the sample mean represent the P of what? The 16. The sample mean is again, like I tell you, the sample mean is going to talking about the 50% and the 50%. So that is going to be 50% reliability and 50% probability to failure. So the sample mean gonna represent the probability to failure of 0.5. Okay, 0.5. Let me accept the phone. Hello. ครับ 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 กี่โมงเอ่ย โอเค ครับ อาจารย์จะไปอยู่ครับ ครับ 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 ส่งหนังสือมาทางไลน์ ครับ ครับ โอเค ครับ โอเค ครับ ครับ สวัสดี Okay, next, the 17, again, if they said, what the sample mean represent the reliability of this? So, you guys know about this for sure. It's going to be what? It's going to be 0.5 of this one. Okay, that's going to be simple to you guys, right? And then coming into this relationship, which equation do give the smallest value of the probability to failure? Again, we come to the normal distribution. And then when we have this, we're going to say about this is going to be represent the x bar. This is going to represent the x bar minus 1 SD. That is going to be the C value. This is going to be the x bar minus 2 SD. So when we do this, we can compute depend on what? If we like to have the smallest probability to failure, that means we're going to reduce this part. If you would like to reduce this part, the value of this coefficient, the C coefficient, supposed to be getting larger. So the result of this is going to be what? A, B, C, D, E. Which one? You know about this for sure. This is going to be what? Going to be this one, right? It's going to be the largest one. This is going to be x bar minus 4 SD. Ajahn is supposed to talk about one more thing. This mu is going to be theoretical mean, and x bar is going to be sample mean. Okay, and this is going to be theoretical standard deviation, and this is going to be sample standard deviation. They are different between the theoretical one and the one that we do the testing. Okay, but they can use interchangeably most of the time. And next on the 19th, there is a guy who's chatting me. Okay, that's good. Some people answer to me. I won't have a chance to take a look at this. Okay, next, which equation do give the highest value of reliability? Which one going to get the highest value of reliability? The value of reliability, again, we talking about the area that's in the right hand side of this graph. Okay, if we like to have the highest value of reliability, that means we're going to get which one? The value of this supposed to be mu minus 4 sigma, right? Or x bar minus 4 standard deviation. If you go further like this, you're going to get a larger orange area. So this one, you're gonna answer with the A. Okay? Okay, and then come to another question. In the quality control testing of material, that is when you work in a factory such as in the steel industry, you produce steel and you test your steel, and you're supposed to test your steel with a lot of sample. Okay, if you test your steel and then you get this normal distribution and you get the mean of the yielding stress of 250 megapascal, and you get the SD of this for 10 megapascal. Okay, when you use the mean to represent this one, that is going to be half of the sample going to be reliable, another half will not reliable. By doing this, you may increase the reliability again by reduce this one to use the value of 250 minus 10, that's 240. When you use 240, you can see the reliability area get larger. And if you use this for this one going to be 250 minus 20, that's 230 megapascal, you will get more reliable. So the question is, in the quality testing of the material, why do we use this equation to find the yielding stress of the steel instead of the sample mean. Why? That means we're going to do what? We're going to increase the reliability of the yielding of this yielding stress. Okay. And are you going to increase the probability of failure? No, you're going to reduce or decrease, okay, the probability to failure, like I mentioned about it. And when you increase the reliability, you also increase the safety factor of the yielding stress. So by doing this, you're supposed to say when you use this mean minus C standard deviation, you're going to increase the reliability, you're going to reduce the probability to failure, and you're going to increase the safety factor of the mechanical property using in your quality controlling test. Okay, and this is a graph that shows you something about what I draw over here. Next, the problem 21. According to the above normal distribution diagram, what do the value of P in percent that the term mu minus sigma represent? That is what? That's mu minus sigma. This means it's going to be the C is equal to 1. When the C is equal to 1, it means this is the C is here. Okay, the value of this is minus 1. This is going to be minus 1. And then what we have represent is what? Is the probability to failure is going to represent this probability to failure, right? So the P is going to be 1 minus R. And if you combine this together, this area together, you will get it for 15.9. Or if you just minus it, this is going to be 1 minus this one, this one, this one, this one, and this one. And that means you're going to minus about 84.1. Okay, and then you will get the same value here. Okay, and come to the next problem. Come to what? According to above normal distribution diagram. Okay, coming into this diagram again. And then what do the value of reliability? This time they ask reliability for mu minus 2 standard deviation. That means what? That means we're going to find the value of this one. Okay, that is going to be mean minus 2 times standard deviation. You compute for this area, and that is going to be what? This is going to be the reliability, going to be 1 minus 0.0214, and then minus 0.00135, and you're going to get it for about 97.7. That's going to be the reliability when you use the mu minus 2 times of standard deviation. And come to the 23rd. The probability to failure is 10%. Okay, and probability to failure is 10% is the ratio of the probability to failure of 1/10. Okay, if the probability to failure is 0.01%, what is the ratio of the probability to failure in this case? So this is going to be what? This is going to be 0.1, right? So what the computation of this is going to be what? It's going to be 1 divided by this is going to compute in 0.01. That means it's going to be 1 in what? 1 in how many? Okay. If you put this one, it's going to be 0.000001. Okay. Take the percent out. The P is going to be this one. And then when you compute this, it's going to be what? The inverse of this is going to be 1 over 10,000. That is going to be 10 minus 4. So the answer supposed to be here. Okay. Okay, this is the P equal to 10% is 110. Okay. If this one, that is going to be 10 minus 4. Okay, that is going to be 1 over 10,000. Okay, and then we come to the reliability 99%. We come to the reliability of 99%. Reliability of 99% is going to be equal to the probability of failure of 1%. The 1% probability failure is going to be 1 over 100. Okay, if it's going to be 0.1%, that is 1 over 1,000. If it's 0.001%, it's 10,000. Okay, and then by doing it, if the reliability is 90%, the probability failure is going to be P equal to 1 minus A. That is P equal to 1 minus 0.9. That is going to be probability failure of 0.1. If this is 0.1 is going to be 10%. Okay, when it's going to 10%, it's come to over here. That is going to be 110. Okay, that is all for the chapter 2. And you're going to do some computation. And I'm going to ask you to go back to check your understanding about the probability to failure P and the reliability, that is the R, okay, and the one equal to P plus R. Coming to next on the chapter 3, the testing procedure. In testing of material, what is the most important mechanical property that will be used in the design of the structure? Okay, for example, if you have the beam like this and it's subjected to 10 kilonewton with the span here of 2 meter and 2 meter. By doing this, you can compute this is 5 kilonewton and this is 5 kilonewton. And then you're going to draw this shear diagram, you find the Vmax, and you're going to draw this one to find the Mmax. Okay, and then this is engine static. Coming to mechanics of material, you're going to set sigma max equal to M max y over I. That is going to be equal to sigma allowed. The sigma allowed is going to be sigma sub y divided by factor of safety. So most of the time when we come to the design of a structure, we first focus on what? On the strength of the material that we are using. And then after you decide it, you're going to get the section. And then you check for what? You check for the tau max, which is going to be less than tau allowed, which is going to be the shear strength divided by factor of safety. So most of the time we consider the strength of the material is the first mechanical property we are using in our design. And the second one going to be checked for the deflection, because under the application of the force, what we have is the beam going to deflect like this. And then we're going to get this one for the maximum deflection. Okay, and then the deflection is going to be what? Less than or equal to L over, if there is no wall here, 240. If there is the wall underkit, it's going to be L divided by 360. And to compute Vmax of this, Vmax is going to be PL cubed over 48 EI. And then what important is going to be the one of this. It's going to be what? It's going to be the modulus of elasticity. That is the next step. We're going to first the first one, the second one, and the third one when we design the structure. These two, this bases on what so-called the strength design. Okay, and this one is based on the stiffness design. Okay, and then come to the problem 26. In testing of a material, what is the most important mechanical property that will be used in the design? This is what going to be what? Ductility? Not really. Okay. Deflection? Not really. And then I just mentioned about this modulus of elasticity. This modulus of elasticity is the stiffness of the beam. So this is going to be the answer for the problem 26. Okay. Now come to the next problem. Number 27. Okay, here comes is a problem number 7. What is the ability of material to resist the applied force without failure? Okay, that is the ability of the material that's resist the applied force without failure. So what we call it strength, stiffness, permanence, plasticity, elasticity. Elasticity is the ability of the material that can deform without permanence. Okay. Plasticity is the mechanical property of the material that may have the permanence. Okay, the permanence before the failure of the material. If the structure, for example, the material stress and the strain, and then one has the graph that has this property and then has this property. Okay, we measure the elasticity of the material over here. We measure the plasticity of the material over here. And then if we have the material, that one is in orange and another one is in pink. Okay, when we compare it, the material, the orange material may have the larger elasticity, but going to have a smaller plasticity compared to the pink one. Okay, they are the different thing. And the permanent set is the permanent deformation when the material has the plastic behavior. Okay, the stiffness is the ability of the material, to what? To resist the deformation. This is going to be resist the deformation under applied load. So when we're talking about this one, we're going to talking about the strength, and usually we use the sigma sub y as the strength of material, and by doing that we use the sigma equal to the yielding divided by factor of safety that represent the strength of the material. And the next one, this one is ability of the material to resist the applied force. And the next one we have what? we have the ability of the material to resist the deformation under the applied force. So this is going to be the stiffness, and then we use the E, which is the modulus of elasticity of the material. And the modulus of elasticity compute from where? Compute from the slope of the graph during what? During the linear elastic behavior. But most of the time, this is going to be equal to delta stress divided by delta strain. And then we have E sub ST about 200 gigapascal. Okay. And we have the sigma sub Y of steel for the typical A36. That is going to be 250 megapascal. Okay. And then they ask us, what is the ability of the material to deform under the applied force without permanent deformation? I said, that is without permanent deformation. That is without permanent set. So this is going to be the elasticity of the material. Okay, so this is going to ask you to understand or feel about some technical term, about strength, about stiffness, okay, about the plasticity, about the elasticity of the material. And then coming to the 30, they ask you, what is the ability of structural steel to resist the deformation? So which one is going to be what? To resist the deformation. That is going to be the property of this one. Okay, this is going to be 200 gigapascal. You got to answer this correctly. I believe you guys can understand this. This is not that hard. Okay, just you guys to check what we have. And then come to the problem 31st. The loading method on the specimen is classified into 5 types. Okay, we have what in our lab? We have the total of 5 types. That is going to be tension, compression, shear test, fractional test, and what torsional test. Which one is going to be what we have? Exactly. It's going to be kind of, yeah, we have the tension test for sure, we have the compression test for sure, and we have this one for lab number 3, we have this one for lab number 4, and this one we have the lab, right? So the answer is supposed to be this one, and we supposed to put the direct shear. We have the direct shear test, and we have the torsion test. We have the direct shear test for the timber, and we have the direct shear test for the brass, for the copper, and for the aluminum. Okay. 32. Mechanical properties of the material depend on the environment. Okay, that is going to be depend on the environment, such as in the sea water, for example, sea water. Okay, or the water treatment plant. What kind of element that we need to consider in the test? Okay, that may be for sea water, you're going to have some kind of the moisture for sure, and in the water treatment plant, you're going to consider the chemical agent that's in the wastewater. Okay, and sometimes when you're talking about the working in the cold weather, okay, if you work in the company PTTEP, you go to explore to find some natural gas from crude oil in the area of North Pole. So your structure may subjected to the low temperature. Or if you work in the steel steel production company, the material in the steel production company may subjected to the high temperature. So when we talking about the environment, we talking at least for the chemical agent, for the moisture, and for the temperature. Okay, we consider all this as specified in the PowerPoint. Next, we come to this one, number problem 33. In selection of laboratory, we select a laboratory to test the construction material, such as if you prefer to select the SUT laboratory. Okay, which factor should we consider? We're going to consider the reliability, right, of the test. When we check for the reliability of the test, we check for the coefficient of elimination, which is going to be the standard deviation divided by the mean times 100%. We also talking about the cost of testing. Okay, we're going to select the one that have a proper cost, and we're going to following the standard. This is very important because when we talking about the construction material, we are going to follow the Thailand industrial standard. Okay, and then for this one, accuracy and precision of the test, that is also important. So we got to select all of the above. Okay, we select everything. When we select one, that's going to follow the TAS. And you're going to check for some kind of like calibration certificate of the testing machine also. The testing machine is supposed to be calibrated for some specific interval of time. 34. What is the error that can be both larger and smaller than the value? Okay, the error, when we talking about the error, we have two things. One is the systematic error. Okay, and another one we call it accidental error, or another name, this one is going to be the random error. Okay, the one that can be both larger and smaller value, that means it's going to be the random error. It can be anything. So you just put this one is random. Okay, when it's systematic, it's going to be one size. It could be one side. For example, if your motorcycle, okay, can let me focus. If your motorcycle show the speed of 100 kilometers per hour, and then there is a police radar tell this is going to be 100 kilometers per hour, then if you dive for 90 kilonewton per meter, so the real thing gonna be computed by this proportion, and then you can compute this one. This is called the systematic error. Okay. Next, how do we analyze to try to correct the error of problem number 34? How can we correct this one? We supposed to use the what for the systematic error. We can do by the proportion. For the random error, we must do the statistical analysis. Okay, to make it use the statistic to taking care of that kind of error. Use the mean, use the standard deviation, and use the reliability. Okay, if you like to have a higher reliability, you have the value of x bar minus some specific CSD, if this one is large, your reliability of the testing result going to get larger, and then that means you're going to take care of the error. Okay, most of your specimen, if you use low value of the data from the test, for example, if you use the value of this, that means the property of your structure, that of your material that won't pass some specific value is going to be small compared to the one that passing it. Okay, you can take care of this error. And then what is the characteristic of the systematic error? As we know, the systematic error is going to be systematic. That means it's going to be on only one side of the real value. That means if your equipment measure 100 and the standard give you 110, and then when you do this with your equipment of this one is going to be proportion, and it's going to be how many? That is going to be 110 times 0.9. If you push it into your calculator, 110 times 0.9, that is going to be 99. And then you can see the answer is 99 kilometers per hour. The answer is larger than this, and this one also larger than this. So the error going to take only one side of the real value of this. Okay. 37. What is the characteristic of the accidental error? When we come to the accidental error, that is going to be the random error. So the earliest kind of error going to be what? It can be both larger or the smaller of the real value. If you have a specimen and then you give 5 of your friend, measure it, it's going to be total of 5 value. And most of the time, you will say just 10.15. Another one may say 10.13. One said 10.16. Another one said 10.14. Another one said 10.17. Most of the time, they wouldn't get the same value. But you can see the value just maybe in the smaller or larger is randomly occur. And 38, what is the characteristic of the random error? And that is the same thing as the above, right? Yeah, the answer is going to be this one. Okay, it's going to be easier for you guys to answer it. Okay, next going to be the 39. We come to 39. Okay, I'm doing some mistake. We're going to have examination from the chapter 1 to chapter 4, not chapter 3. Okay, that is going to be close to the end of chapter 3. A car, okay, have a speed of 100 kilonewton per meter. Okay, official speedometer show that your car going to be just only 99 kilometers per hour. If the error is systematic, if your car drive for 110, what should be the speedometer of the car show? Just 100. That is 99. This is 110. Just 110 times 99 divided by 100. You get the answer of this. Okay, just do the proportion because this is a systematic error. A car has a real speed again of 100, and then it said the speedometer your is 101. Okay, and then again you can do the computation for this for sure. Okay, I let you guys do it by yourself. This is really easy. And the last chapter for the midterm examination going to be chapter number 4. So what is the elongation or contraction of a line segment of material per unit length? That is going to be this deformation divided by the L under the application of the force. This is going to be the normal strain for sure. Okay, the definition of this, you can see it. And then what is the intensity of the internal force on a specific area? When it said intensity, okay, that is going to be the normal stress. Okay, and 43, this is going to be the stress, sorry, this is not normal stress. Normal stress is going to tell about something more specific on this. Okay, this is just the stress. For the normal stress, this is going to be can be tau equal to V over A or sigma equal to P over A. This is going to be the normal stress. So the intensity of the internal normal force, that is P, okay, acting on the small area. So this is going to be the normal stress. So be careful about this. Okay, don't decide the answer so quickly. You may make a mistake like the one that I just did on this. Okay, and then we go further to chapter 4 and problem 44. What is the intensity of the internal? Oh, this is shear force. So this is tau equal to V over A. So the answer is going to be shear stress. Okay. And then they ask us which one in the unit of this. You know the Newton per square millimeter is equivalent to megapascal, right? Okay, this is going to be Newton per square millimeter. It's going to be 10 power 6 Newton per square meter. And you know that the 1000 millimeter, that's equal to 1 meter if you power it by 2. And then it's going to be 1 square meter is okay to be 10 power 6 square millimeter. Okay, and then it's going to be equal like this. And what is the value, the mechanical property that has the unit of megapascal? This one usually has gigapascal. The shear strain is going to be in radian. Elongation may be meter or millimeter. The shear stress, yeah, this one, okay. The deformation may be meter, millimeter, or if it is the rotation, it may be the radian. Okay, so this is going to be the answer. And 45, which of the following has a unit of measurement this is easy. This is meter by meter, or you may say this may be meter by meter, meter by meter is the same thing. It's going to be what? It's going to be the normal state, right? It's not going to be shear strain. Shear strain is going to be in the radian, as we specified before. And the other deformation also going to be just the length, elongation only the length, meter, millimeter, meter, millimeter. And 47, which of the following has the unit of radian? As we show, this is going to be the shear strain. Okay. And 48, which is the change in angle that occur between two line segments? Before this is going to be have this normal, and then after the application of the force, this is going to change the angle into this. So no, it's not stress. This is the change in angle, not stress. Okay, and then it's going to be this is start from the normal angle, the red one, and then to the one under the applied force. This one going to be the shear strain. We have the gamma equal to pi over 2 minus theta star. This is going to be theta star. That is going to be the shear strain. Okay, and then we come to the problem 49. Problem 49, we have a graph. Okay, from the stress strain diagram of the mild steel as shown. What is the region where the grain of steel rearrange itself. Okay, you got to understand the behavior of this one can be classified into elastic, and the other is classified into the plastic. And then in this plastic is also classified into this one as the yielding. Okay, and this one this one called the stain hardening. Okay, and the last one that show the neck, they call this one is the necking. Okay, so which one let's show the arrange of the grain, that is going to be the yielding. Okay, during this behavior, the grain of this steel just rearrange itself to get it more compact. When then the grain get compact, and then they come to the stain hardening region. Okay, next, from the stress strain diagram of my steel astro, the ultimate stress is the end of which behavior. The ultimate stress is going to be this point. Okay, the ultimate stress is the end of this behavior, is the end of stain hardening behavior for sure. Okay, 51, from the stress strain diagram again, the ultimate stress is the start of which behavior? Is going to be the start of this behavior of necking. So this one you got to answer to be the necking. Okay, and from the stress strain diagram of the steel astro, the yielding is the end of which behavior? The yielding is the end of which behavior? The yielding is not the end of behavior. The yielding is the end of its behavior. The yielding support in the start of which behavior of the steel? Which one? The yielding. The yielding is going to be which behavior? The yielding is ending here. Okay, the end of the yielding. The end of the yielding is the start of stain hardening. Okay, this is going to be the stain hardening. And then come to the author. We have a lot of them. 53. And again, we have 1.5 hours to work on. Now we come to the 53. From the stress strain diagram as shown, yielding stress of the material, of this steel, what is this? This is what? This is the stress strain diagram that didn't show the yielding point. We got to use the 0% offset to determine it. We just come to this. 0.2% is 0 divided by 100. That is going to be 0.002 millimeter by millimeter. That is going to be about this. And then we got to draw this one parallel to this portion. Okay, and some people are very genius. Just put this one for what? For 7 millimeter. Just put this one for 7 millimeter. And then by doing this, you're going to get it in parallel for sure. And then when it's come here, you just take this one in parallel to the vertical axis and put it over here. Okay, for this one, you can see the value is this, no. This is no. And this is no. So about which one? The 330 and 350. So what do you think? What is going to be? The 330 supposed to be about this, right? So we got this for 350. Okay, so you have a chance to practice to determine the yielding stress of the material. Okay, and then what is the material that can be deformed considerably, that's deformed a lot before the failure? Okay, this is going to be two types of the material, the ductile and the brittle material. The brittle material such as the concrete, okay, such as the cast iron, when this subjected to the tension, it can fail abruptly. That is the brittle. The material that can be formed a lot is going to be the ductile material, such as aluminum, such as the steel. Okay, and then what is the material that has small or no yielding? This is simple. That is going to be the brittle material. Okay, which material can be deformed considerably before its failure? It's the same as 54, but this time they just put it into the type of the material. No, it's one. This one is one. This one is one. So you have the timber and the aluminum. Which one is clearer? For sure, you guys answer this. The aluminum going to be clearer. And then the 57, which material have small or no yielding before the failure? Which one? This yield a lot. Okay, this yield a lot. And this also yield a lot. This is rubber yield a lot. So there is the stone and the timber. You just said it's supposed to be the stone. Stone very similar to the concrete. Okay, it can fail abruptly in some, especially in tension. And go further to problem 58. Okay, in the problem 58, which equation is used to find the percent elongation in tension? Okay, we have the tension material. After the failure, this specimen will have a kind of necking, and then when you put them back together, you measure this one to be L sub F, and this one is the L sub O. Okay, and then the equation is going to be L sub F minus L sub O divided by L sub O times 100%. That is going to be percent elongation. This is going to be percent elongation. Or Ajahn may give you, this is going to be 100 millimeter, and after failure, this is going to be 111 millimeter. What is going to be percent elongation? Is going to be 111 minus 110 divided by 110 and times 100%. That is going to be the percent elongation. Okay, if I ask you about the equation, just give the equation. If one, just do some computation. Okay, and the same thing occurs for this one. You can measure for the D sub O, and then you can compute A sub O equal to pi D sub O square divided by 4. Okay, and then you can measure this one. This called D sub F, and this one going to be A sub F pi D sub F square divided by 4. The same thing of this, just A sub F, the percent reduction A sub F minus A sub O divided by A sub O times 100%. Okay, and then it may say this is going to be 5 millimeter, 5 millimeter, and this is going to be 3.5 millimeter. Can you compute for the percent reduction of the area? Yes, for sure. This is going to be pi and then 5 square over 4 minus pi and then t.5 square over 4 divided by pi and then t.5 square over 4 and then have 100%. You will get this in the percent. And most of the time I should say this is going to be positive value and this is going to be negative value. So this one you may have a sub f minus a sub o divided by a sub o, or you may need to do some computation if I give you the dimension of the specimen. Okay. Okay. Come to the 60. What material have small or no yielding before its failure? Very similar to one previously. This is going to be small and no yielding. That is going to be the brittle material. Which one is going to be? This is not. This is not. This is not. This is not. And then you can answer for this is going to be cast iron. Which material has the highest tensile yielding strength? Okay, and the yielding, the highest tensile yielding, and this has no yielding. This has no yielding. Okay, this is has very high for the compression, but this is for the tension. This is not. This is not. So this is supposed to be the steel. Okay. That I may say when we consider the E is going to be the stiffness, right? Okay. Which material has the highest stiffness? Okay, based upon this one. This one going to have the highest stiffness. Okay. And which material gonna have the lowest stiffness? Which one going to provide the lowest stiffness? The concrete and the brick supposed to be similar. The steel and the cast iron supposed to be similar. Most of the time, the lowest supposed to be the wood. Okay, I may ask you something like this, not just this highest strength. I may ask you the largest. Okay, the LAR, the largest stiffness, or the smallest, or the smallest stiffness, the lowest, or the lowest stiffness. Okay, so you may answer about this. Okay, and then a little bit further, just move to next problem 62. Problem 62. On the problem 62, I may ask you, which of the following is correct? Which one is correct? Which one is correct? The modulus of elasticity of a material is the slope at any point of the state diagram. No, it's going to be the slope only in this linear elastic region. This is not correct. The modulus of elasticity of material can be determined in the yielding region. We cannot determine the modulus of elasticity in this region. Okay, and the modulus of elasticity of material is the stiffness. Is show the stiffness for sure. This is going to be show the stiffness of the material, and the E sub S is about 200 gigapascal. And if you have the E for the aluminum, let's say for the aluminum, that is going to be about 70 gigapascal. And then you have the E for the concrete, that's maybe 20 to 30 gigapascal. And I can ask you again, which material gonna have the largest stiffness? Okay, or you may answer this is going to be the largest stiffness. If you have smallest one, this is smallest one. Okay. Okay, the author is wrong. The modulus of elasticity depends on the value. It's one depend on the value. Okay, it's just depend on the value of slope. And most of elasticity indicate the strength. No, strength indicate by the sigma sub y for the steel. Okay, or indicate by sigma ultimate for the concrete. Okay, next, which material has the highest compressive ultimate strength? Okay, and you may say most of the material, if we test like concrete, if we test in tension, it will have very small strength, but when we test it in compression, it may get the highest strength. This is positive, this is negative. Why? The brittle material has this kind of behavior, the brittle material such as the cast iron. Okay, the cast iron have the carbon inside it. Okay, so the carbon and steel, when it stay together, it has the micro crack. When you put this in tension, the micro crack just open, and then the area of the cast iron that resists the tension just get smaller and smaller, and then the cast iron fell brittle or abruptly failure in tension. However, when you put the cast iron in compression, the micro crack close, okay, each other, and then there is the Poisson effect that's going to expand the specimen a little bit. So the area of the specimen also get larger by causing the micro crack, and larger cross-sectional area. The behavior of this cast iron going to be like this one. So the highest compressive going to be what? Going to be the cast iron, not the wood, not the brick, not the concrete, and not the rubber for sure. And which material has the highest modulus of elasticity? The E of the concrete again is going to be 20 to 30 gigapascal, and E of plastic going to be about maybe like 1 to 5 gigapascal. The wood, the E of the wood is maybe 5 to 10 gigapascal, and the brick may be close to the concrete. For the aluminum, that is supposed to be 70 gigapascal. Or you may see the state diagram from the PowerPoint to make the decision on this problem 64. And now come to the 65. Theoretically, the Hooke's law can be used only for the proportional limit. Why? Because Hooke's law said stress equal to modulus of elasticity times the strain. That means it's going to be the what? The slope in this linear elastic region. Why the design code allow us to use Hooke's law up to the yielding point? Okay, first, the yielding can define clearly. So, example, you may determine the clearing for 0.2% offset that's specified from the specification, like for example the TS or the ASTM. The yielding point has higher magnitude than the proportion. But it's not that much different, right? And the proportion limit point has higher magnitude. No, most of the time this is lower. Okay, the lower. The yielding has the higher. And the yielding point represent the stiffness. No, this is not represent the stiffness. A and D. This is not correct for sure. So what we supposed to answer, this is not correct. It's going to be just the A. Okay, for this. The yielding point has higher magnitude than the proportional limit, but it's not that much. Okay, it's going to be very similar to each other. Just go to check the stress strain diagram of this structural steel. 64. What is the advantage of strain hardening? The strain hardening is what? The strain hardening is the behavior of the material. When we have this kind of material and then you load it and then passing to the elastic, you go to this into the plastic region, and then when you release the force, the curve just go back in this one, and then the stress strain diagram just change into this. What happened is usually we have the yielding here, but by using the strain hardening, the yielding just increase like this. So it won't increase the elongation. It won't increase the fractional stress. It's going to be the same fractional stress. It's going to increase the yielding like this. Okay. It's not increase the hardness. Okay. It's not increase the stiffness because the slope here and slope here, they are equal. Okay. So you answer this. 67. Which material is the best to be strain hardened? Okay, which one you prefer to do this? The plastic, no. The cast iron, this is brittle material. This is brittle material. The wood have linear elastic to failure. So the material that has this kind of stress strain behavior is the aluminum alloy. Okay, and then further question just come to the 68. Okay, 68. That's a lot of question. The 68. 68. We come the modulus of resilience. The modulus of resilience is what? The modulus of resilience is the area under the stress strain diagram when the material has linear elastic behavior is computed by this area. So it is not the strength because the strength is the sigma sub y here. It is not the stiffness because the stiffness is going to be the slope here. It is not the plasticity. It's going to show this is the plasticity. It is not the elasticity. The elasticity is here. So it's going to be the energy capacity of the material during its linear elastic behavior. And then what the modulus of toughness? Okay, what's of toughness? Loss of toughness also. Loss of toughness is the whole area of under the stress strain diagram. That is going to be the energy again, right? It's the energy of capacity again. And then we have another thing. We have the modulus of rupture. Modulus of rupture is what? Modulus of rupture is the stress of stress, the stress maximum when you do this kind of fractional test. So most of the time, if we're talking about the modulus of rupture, is the strength of the material under bending or under flexion. Okay, it's different from the strength of material under tension. This is the strength of material under flexion. Okay, then come to the Poisson ratio, which is the equation from the Poisson ratio. Okay, one ratio always has the negative sign, right? So they're going to have these two equations. And then Poisson ratio has the value between 0 and 0.5. Why? Okay, Poisson ratio, when you pull the steel will get longer, but the steel also has the contraction, lateral contraction. This is called lateral contraction. So Poisson ratio is going to be the equation of this. Okay, and For the zero, the Poisson ratio that's close to zero, we're going to have that for the concrete or for the rock. Okay, the material that has Poisson ratio close to 0.5, that is going to be the rubber. Okay, we did this for the lab number 2. And what is the Poisson ratio for the steel? That is about 0.28 to 0.22. So the Poisson ratio of steel is in the middle of the concrete and of the rubber. Okay, and then which material has the Poisson ratio close to 0.5? Okay, this one. Okay, this is going to be close to 0. This also close to 0. Okay, this is about 0.3. Which material has the Poisson ratio where you close to 0? So this is going to be the stone. Okay, stone or the concrete is maybe the stone or the concrete is depend. And then come to the next of this is 73. What do we call failure mode? The material failure due to the decreasing of high tensile stress that acts on the metal for a long time. So what is this is you have the stress and you have this one, and then you put this stress up to here, and then stress just decreasing of the high stress. This occur in what? This occur in the pre-stresses, okay, wire. Most of the time we put it in high stress. And then this is called what? This is called the relaxation, the grain of the pre-stresses, wire just move when it's subject to the high stress for long duration, okay? This is what I just mentioned about if your mom have a wire on the back of your house to put the wet coat onto it. Okay, sometimes when she use it for a while, the wire will get relaxed. Okay, relaxation, and then the ability, the inability and elastic failure of the column under compression. That's going to be what? The column when is subjected to this. For the short column, is going to have the material failure. For the long column, it will be like this. That's called the buckling. Okay, that's called the buckling of the column. And then 75. What is called the mode of failure? Structural member and metal part that fail abruptly under the action of the repeated stress. We have this one in the chapter in the laboratory 13, right? And is subjected to repeated stress that's less than the yielding stress. This is called the fatigue, right? And then the last one, what do we call the mode of failure when the material fail due to the permanent deformation? That is continuously increased in some materials such as the concrete until the structure cannot perform its function as decided. And this is going to be the clean. Okay, and that's those and this 26 problem are the example of what I have asked you senior in the past on the midterm examination. And you can see some of this require you to remember. Some of this require you to understand the definition, understand the application. And also some of this require your sense of engineering and also require your engineering judgment. So we are going to have about 60 to 70 problems for the midterm examination. And I hope you guys study the 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 PowerPoint or the book and also the laboratory manual. And I recommend you guys again to take a note for the examination. And I hope you guys success in the examination. And that's all I have for today. And since it has only 20 more minutes to 25 more minutes till 3 p.m., the rest of the lecture of chapter 5 I will postpone to the next lecture, and I will let you to have times to study, review what I have over here. Okay, have a good day, and then see you guys on Thursday on the theory of structure. And today just finish it here. Okay, thank you very much. Enjoy your afternoon and taking care of yourself. Okay, bye bye.